you look for? Geometry. Close. You're actually looking for more specifically. Does anyone remember? There's a specific number you're looking for. You do it almost every time you find molecular geometry. Yes, steric. Yes, exactly. See, you guys are like right on the edge. Steric numbers, exactly. And you use the electron and molecular geometries with that. So you'll find the steric number with that. And how do we calculate steric number? And this should be pretty fast. You guys know this, right? Steric number. How do we do that? Of like C2 or something. How do we find that? What's the first thing you add? Yes, exactly. Bonds plus, or like the number of atoms attached to the central atom, and then plus the lone pairs attached to that central atom as well. So what's electron pair geometry speaking of? How do we find that? What is it specifically, like definition-wise? Because the last test, some people had questions on like definitions. They didn't know specifically what to put. So what's electron pair geometry? Right? So if you have C2, what is that? Like electron pair, right? Because that's linear from what we're looking at. So what does that explain? Does anyone want to take a stab at it? Just guess.
Like...
If you don't know, you can always just guess. Wrong answers are fine as well. Does anyone know? Yes, no, I don't know. You're looking for the geometry of it. So the structure of it, right? But not the atoms itself. Does anyone know? Number of bonds, shape. Okay, so the number of bonds, yes, Jorge, that is correct. Part of it, actually. And then the atom's essence, that's used more in molecular geometry, which we'll get to. So electron pair geometry, electron domains, yeah, similar to that as well. So it's actually a 3D arrangement of the bonding pairs and lone pairs. So it's not just the bonding pairs, but you're using the lone pairs as well. And those are both included. And molecular geometry, does anyone know? It's very similar to what Essence said. What is that the arrangement of? Does anyone remember? Because it's not bonds, right? Because the bonds is the electron pair. So what's molecular then? What are you looking for when you do molecular geometry? You're looking for the arrangement of what? The angles? Well, not exactly the angles. You're looking for the arrangement of the... You're looking for like the C2. So what is that? If you're looking just for the C, what are those called? Molecules. Yes, you're looking for the 3D arrangement of the atoms or the molecules or particles specifically. So, speaking of which, the geometry, what are the 5 common shapes that you're using? And you guys don't get an equation sheet, right? So what are the 5 common shapes? What do we have? Like steric number 3 or 4 or 5, like what are the shapes of it? Tetrahedral, linear. Okay, yes. Linear is for 2, tetrahedral 4, trigonal planar. Yep, what else is there? You guys are missing 2 more, I believe. Octahedral, yes. And was there something else? Anything else? Yes, exactly. So that would be 5 of them. We have linear, Chris said, trigonal planar, Sierra, and then tetrahedral as well. Octahedral, and then we have trigonal bipyramidal. So if you have symmetrical Lewis structures, what are those bonds? Does anyone remember? Symmetrical. That's nonpolar. Okay, and do we all agree with that? Do we all agree with Akash it's nonpolar? Yes, okay, exactly. Yep, it's nonpolar. What about asymmetrical? What is that going to be then? Right, because it's nonpolar for symmetrical. What's asymmetrical? Polar. Yes, exactly. It's going to be polar. So now that we've found that, how else will you determine it? Because we know symmetrical and asymmetrical, right? But if you're just looking at it and you're like running out of time on a test, and let's say you have like 5 minutes left and you have like 10 questions, like how would you just know looking at it? Like what else would you determine? Right? Because that's not the only way, right? Bonds. Okay. Yeah, that's good. You can use electronegativities. Yes, exactly. Hydrogen bonds. And hydrogen bonds, like what's included in a hydrogen bond? Yeah, exactly. And also, molecular geometries. With geometry, will always be polar. You guys know? Like, if you ever find this bent, exactly. If it's bent and you find that as a molecular geometry, you always know it's gonna be polar. It will always be polar. And then, what else is there? Like, let's see, CH8. Is that polar or non-polar? Non-polar. How do you know? How do you figure that out? Right? Because I don't think anyone just drew a Lewis structure, right? How do you know? Immediately, like right off the bat, how do you know that's polar or non-polar? Symmetrical? What else? Does anyone know? H bond. Okay, yeah. With this specifically, I would reserve those H bonds specifically just for hydrogen bonding. Yeah. Actually, I would go more specifically with what Jorge said, that CH bonds are always, and just CH bonds alone are always nonpolar, like always, all the time. And so other ways you would know was, I think someone said like just having it alone as well. Like if you have just one singular element like Cl or Br or something, that again, there's nothing to bond to, there's nothing there, it's just nonpolar. What else would you know? Symmetrical, yeah. Metal. Yep, exactly. So there's actually a list I'm gonna show, but yeah, so this is the first answer. You can see steric numbers, 3D arrangement of atoms versus bonding pairs and lone pairs, things like that. And then here's the picture. I found this really helpful. So hydrogen bonding, H, which I think Essen said, H attached to nitrogen, oxygen, fluorine, it'll always have a polar bond in there. Yeah, Khan Academy. Yeah. Oh no, actually this is our organic chemistry tutor, but Khan Academy is also nice. Also, any element that's doubled, so N2, Cl, something like that, that will always be nonpolar as well. So if you see that in just alone, then you know that's nonpolar. Any element alone is nonpolar as well. Same. This is what I used when I did Chem 1211. CH, just alone, again, nonpolar. Also, if you have CH and you have like OH together, the CH, it doesn't matter anymore. The OH is what matters, and that's hydrogen, so that will be polar instead. Again, CH, it only works if it's alone. It doesn't work if there's like an OH or an NH2 or something. It doesn't work anymore. So there's limitations. And again, like symmetrical, like this one that he circled, you can see the electronegativities are positive. It's hard to say because I've memorized these and I thought like, oh, I got it or whatever. But when you're doing it under a time constraint, it can be kind of difficult. And there are limitations to every single like thing. There always are. So you have to take into account those things. But I would suggest memorizing this as well because I think it's helpful. Like CH and stuff, like you'll just know immediately. Like when I see those, I don't even have to think about it anymore. Like I just know that's nonpolar. So are we good on that? That's just a warm up. But I think this chart's pretty simple. Okay, next. Okay, determine the electron geometry, molecular geometry, and bond angle of nitrosyl chloride, which is NaCl. So, doing that first, what's the Lewis structure gonna look like? And I'll draw it for you guys because I think that'll be a little easier to see. So we have this, right? What's the number of valence electrons we're gonna have? Does anyone know? How many does oxygen have, for example? How many valence electrons does oxygen? 6, yes. And then Jorge already did all of it because of course. Okay, but N has how many? Does anyone remember? N has 5, yes. And then Cl has how many? Yes, and then Cl has how many? Because we have 5, right? Yes, exactly. Which will equal 18. Yep. So once we do that and we do the structure, what is the electron geometry? What does that look like? And what is it actually? Once you do that, right? Because you have the number of bonds. You have 2 atoms it's added to, right? So you have 2 already. Are there any lone pairs? Does anyone know? Are there any lone pairs on this? NOCl, right? Because you have 18. You put that all there, is there no lone pairs? Okay, do we all agree with that? Do you agree with Chris? Or is there a different answer? Any other lone pairs on this? Right, because you have, can there be a double bond? And then maybe there's a lone pair. So again, I'm gonna open up the floor. Anyone say there's a lone pair? Yes, no, I don't really know. Again, if you don't know, it's okay, you just write it. So does anyone have anything they wanna say? No? Okay, well actually there is a lone pair. And the reason for that is because there's a double bond between N and O. So once you do that, you have those 2 other ones over here. Then you have the 6 over here. Because you still need an octet, right? It only has 2, 4, 6. You need one more, which makes a lone pair. So instead of having just two, and that would be linear, we're gonna have one more, right? So you're gonna have a steric number of 3. And what's that gonna be? Does anyone remember what's that electron geometry coincide with? Trigonal. Yes, exactly. So what is the molecular geometry? Now that you know that's trigonal planar. Yep, Akash and Connor, that's correct. So what's the molecular geometry now? Bent. Yes, exactly, bent. And because it's bent, we know it's what type of bond? What type of bond is that? It's bent. Polar, yes, exactly. So what's the bond angle? If we know it's bent, we know it's trigonal planar, and it probably looks like this. We know that. What's the bond angle? What's that angle?
Oh.
Okay. Okay, so we have some different answers. Does anyone else want to say anything? Because someone said less than 109.5, and then some people said less than 120. So what is it then? What is it? Does anyone have anything else they want to say? Or is that the final? Anything else? Okay, I'm just gonna assume less than 120. Yes, that's actually correct. I think less than 109 is actually associated with a different steric number, but I appreciate the effort. It's actually just less than 120. Yep, correct. So now that we did that, let's do the second one. This one should be a little bit easier, I think. So you have bromine trifluoride. What is the valence electron of all that? What's that gonna be? Right, because we have Br, F. So what's the valence electron on F? Okay, 20. Okay, what's the valence electron on F? Does anyone remember? It's the same one as you. Yep, 7. And then what about Br? 7. Yes, exactly. So once you do all that, you multiply it, the final answer will be 28. Yes. Jorge is just fast. Yeah. But once we do that, how many lone pairs will we have? Because we have 3 attached bonded atoms, right? What are the lone pairs? I kind of want to see like how you guys do bonds and stuff. Like how many lone pairs will we have? Or will we not have any? What will we have? How many lone pairs do we end up having? 1 on Br. Okay, Savannah says 1 on Br. Do we agree with that? Or is there something different? 2 lone pairs. 2. Okay, yes. Actually, it's 2. I think, Savannah, you're almost there. Almost. I think you might have accidentally put another bond in there or something. The IP? Wait, what do you mean by that? Oh, lone pairs, sorry. Lone pairs, yeah. But this, again, like it's just 2 for, you'll have 6 on this one, 6 on this, 6 on that. And then you need more like pairs upon the whole structure, but there's not enough molecules around it. There's not enough Fs. So because Br is the way it is on the periodic table, you can add an extra lone pair on it. It's like one of the exceptions you have. Yeah, so you can add another one. And I know this makes more than just like 04 or whatever, but it's fine. So you end up having 2 lone pairs, which means that you have 5, which is what steric number is that associated with electron geometry? What is that? 5. What is that? Does anyone remember? Trigonal by. Yep, exactly. So what is the molecular geometry with that? Does anyone remember? T-shape. Okay, and did we all agree with that? T-shape. Yes, exactly. Try to ignore it. I don't know if you guys can hear that. There's like something outside. But yeah, it'll just end up being a T. You guys can tell from when you see this and you draw it out, you can actually see the T shape. So it's one of the more unique molecular geometries you'll come across. So do we have any other questions about that part? And if not, what are the bond angles associated with it? So BRF3, what's the bond angle? Because we know it's T-shaped, right? So once we know that, what's the bond angle we're gonna have? Okay, and do we have any other answers or do we agree? Anyone else? Say anything? Like, oh, agree? Okay, agree. Okay, I see. So actually, it's actually narrowed down a little bit more. So instead of just saying, oh, it's 90, 120, or 180, it's actually going to be 90. Yeah, less than 90, actually. Yes, exactly. It's less than 90. We're going to go a little more specific. And usually the bigger the steric number is, the smaller the bond angle will be, because it takes up so much space and it has so many atoms are usually attached to it, or lone pairs. Yeah. So then it'll have smaller spaces where the angles can be. So therefore, with more molecules, a higher steric number, there will be a smaller bond angle associated with it. So once we have that, this is the answer. And then as you can see, those are the lone pairs. I try to choose examples with like more lone pairs on it, so you guys can see how that would work with different molecular geometries. So speaking of, let's label this one out, because I know you guys don't have an equation sheet, so I want you guys to know this immediately. So electron pair geometry, the first, what numbers go down this? What are the possible electron pair geometries that we can put here? Does anyone remember? What's associated with electron pair geometry? 5, okay, yes. What else can be there? 5. Yes, and those numbers will go down until, so I'll go 5, and it'll go all the way down until what number? Does anyone remember? It'll go 5 or 1 until, actually not 1, 2, yes, exactly. And that's kind of like true for everything, actually. You'll see it goes 5, 4, 3, 2. Just, and I think that's what she meant too, like by 1, like it only goes from 5 to 2. And it's the same for all of them. Octahedral, 6, 5, 4, 3, 2. Never 1. And then linear is just 2. It only goes until 2. That's it. It can't go past that. And the number of bonded atoms, what do we get for that? How does it start? There's also a pattern to this one as well. 0. Okay, and then where does it go? How much do we go to? 0, 1, 2, 3. Just go to 5, 6, 1 to 4. Okay, do we have any other answers? So 0 to 4. 3. Okay. Does anyone have any other answers? 3. Okay. Yes, exactly. It's 3. And the reason for this is because it always starts at 0. The number of bonded atoms will start at 0 with the associated pair geometry, right? And then it'll just go the opposite way. 5 will go downward until 2. 0 will keep going and keep increasing until you get to 2 on the other side. That's how you know when to stop. So I think once you know that pattern and you have that memorized, it's easier to understand it. So number of lone pairs. If you have 5, 0, what's the number of lone pairs you'll have? Does anyone remember? Oh wait, that's already there. Wait, that's the wrong column, my bad. Skip that part. Molecular geometry, my bad. Okay, so you have 5, 0, what's the molecular geometry of that? Does anyone remember? Okay, trigonal bipair model, yes, exactly. So what's the next one? 4, 0, 4, 1, what is that? Seesaw, yep. What about 3, 2? We just did this one too. T-shaped, yep. And the molecules would just look probably similar to like something like this. And then usually they'll have like a lone pair or something, and it'll just look like a T. And then 2, 3, what is that? Does anyone remember? Yeah, this one's probably the hardest one to know because there's so many different molecular ones. Chapter 5, yeah, for exam 3, Chapter 5, we're basically doing 5.1 and 5.2 for the most part. It is mainly VSEPR theory, and everything else that goes in with like 5.1 and 5, like it's mainly just VSEPR theory. Like a lot of it, from what I recognize, like recognizing polar, nonpolar, like you use VSEPR. So theoretical bond angles. So you have 5, 0. What is the theoretical bond angle of that? What's that going to be? There's 2 of them too. So what is that going to be? We have 5 and 0, 90 and 120. Okay, very nice. What about 4 and 1? What do we have with that? Does anyone remember? It's very similar to 90 and 120, right? So, yes, exactly. And I believe this is just memorization again. Like it's on your sheet. I think also in the textbook. Like you just have to memorize it. I know it sucks, but you still have until Monday. So that's pretty nice. What about 3, 2? What's 3 and 2 gonna be? I think we just did this one, so yep, less than 90, sorry. And then 2 to 3, what's that gonna be? It was just linear, straight. Yeah, 180, yep. There's no bonding, there's no nothing going on like that. So it's just going to be straight. So that's pretty easy. And then that's what it looks like. So once we've done that, what's the valence bond theory? Conceptually, what is that? Like, put it out into words. What kind of bond is used? Yep. So that's, but also valence bond theory, what is that? Does anyone know the definition? Like, what bond is used in that? Does anyone remember? What type of bonds are we using in valence bond theory? Is it polar, nonpolar, ionic, covalent, metallic? Like, what are we using? Covalent. Yes, exactly, Natalie. It's covalent. And what happens with these covalent bonds? What happens to them? How do they form? Actually, using orbitals, how do they form? Does anyone remember what that is? Like, if you're using those two different like orbitals, like how do we use that to form covalent bonds? Does anyone know? Overlap? Yes, exactly. And what type of orbitals are we overlapping to form those? So if we have like C to C, we have those two orbitals and they're overlapping. What about those orbitals are very unique? SP? You're on the right track. Does anyone know? Yes, no, I don't know. What's special about these orbitals? No, you don't know? Okay. So covalent bonds will form using half-filled orbitals of two different atoms overlapping. So when these half-filled orbitals, that's what I was trying to like show, like, because I thought it would be an easy representation. Half-filled orbitals of two different atoms overlapping to create covalent bonds will become a valence bond theory. Like, that's what the theory is all about. And then that's where you come up with the Lewis structure, the steric number, the formal charge, which you guys did like last test or something. Like, that's what's used in this theory. That's why I would say you would really have to know this because it's pretty much used all the time. And then when I say overlap, what does that mean? Because I have it here, overlapping orbitals, but what does that mean? When you're overlapping, like, for example, like with that bond, combined? No, not combined. What happens with that actually? If you're overlapping it, what happens in that bond? Does anyone know? Hybridized? You're getting there almost. What else? Does anyone else remember? No? Yes, no, I don't know. You're overlapping this little gray area. What's going on? You guys are overthinking it, I think. Does anyone know? No? No, not. You're getting there in a way. When I say, yeah, yes, sharing, you're just basically, when this is overlapping, you're basically just, those orbitals are occupying the same space. That's pretty much it. Again, I think you guys are overthinking it. When it says overlapping, it just means like both of those orbitals occupying the same space or same region. So what about a sigma bond? If you have a sigma bond, what is that? So C to C. What's a sigma bond? A single bond. Yep, that's how you identify it, but what is it? Like, if you're gonna see, like, here obviously, yes, that's a sigma bond, but how would you describe that besides just saying, oh, it's a single bond? What is that single bond representative of? What does that show? Does anyone remember what that is? Two lone pairs? No. Okay, so I think some of you guys might be confused. So, no. Okay, so it's actually going to be the highest electron density between two atoms. That's what a sigma bond shows. The highest electron density between two atoms. And then the pi bond is, does anyone remember pi bonds? Right? Because I know you guys know how to identify those, right? Like if you have a triple bond or a double bond. Pi bonds are actually going to be the highest electrons that you're going to encounter above or below. So instead of being in between, how do you identify them? That's what we're getting to. And I'll show you. Okay, what about hybridization? What's that? Akash will get to that question a little bit. I have it later on, don't worry. So hybridization, what's that? What do we do about the orbitals that we just came across? Hybridization. What do we recognize? What are you doing to those atomic orbitals? Does anyone remember what you're doing? Because I know you guys know how to identify them, but do you know what they are? Yes? No? I guess you guys can just give a guess. Like if you don't know, you can just say like, oh, I think it's this or that. Like it's okay, you have a wrong answer. Any takers? Any combined orbitals? Yeah. Very similar, almost. Not combining, but rather mixing is the right word for it. You're mixing atomic orbitals to create new or form new orbitals in the process. See, if you just guess, you might just get it right. So yeah, you're just basically mixing orbitals to form new orbitals. So once we do that, so those are the answers to that. And so again, like, yeah, you're just forming new sets of orbitals, pretty much. So, and then we're gonna get to this question. I think Akash said, like, how do you identify those? But what's the steric number associated with each hybridization? So you have SP. What's the steric number? Does anyone remember that? What's that gonna be? You have SP2. Okay, and do we all agree with that? It's gonna be 2? Yes? No? Do we all agree? It's 2? Yes, exactly. Yep, it's gonna be 2. So once we have that, what are the sigma bonds associated with it? What's the number? Does anyone know the sigma bond? And once you know this, like it'll be really easy. Again, it's another process. So sigma bonds. What's the number of sigma bonds? You can just guess. You can give me a number. It's okay. Like your best guess. Or what you think. 1. Okay, close. Okay, so I think we're blanking on here, but it's just, yes, it's gonna be 2, exactly. And then what about SP2? What's the steric number? Does anyone know? What is that gonna be? What's the steric number of SP3? 3, yes, exactly. And then the sigma bonds, because I think some of you guys didn't know this, is that it just goes in order. Again, yeah, it's 3 and 2. Yeah, 3 and 2. So it just goes in order, basically. And then what about SP3? What's that gonna be? What's the steric number? 4, yes. And then, yeah, it's actually gonna be opposite. It's gonna be starting with that number, sigma bond, and then you're gonna keep going down to 2. Yeah. Yep, that's correct. 4, 3, 2. That's how you find that part. Pretty simple, right? So again, that's just another pattern. And then what about pi bonds? See, there's a lot of patterns in chemistry. If you recognize it, it becomes way easier to do. So pi bonds, how do we find that? Like Akash asked, like, oh, how do you find that? We have a triple. How many pi bonds do we have here? Does anyone know? You have a triple bond. How many pi bonds do you have? 2, yes. And how did you get 2? How did we get 2 from this? How did we get 2 pi bonds? Does anyone want to say, like, above and below? Yes, exactly. You're going above and below, which means that whatever bond you have, and it's usually pi bonds only come out of double or triple bonds, it'll be 1 less. So you have a triple bond here, you're going to have 2, because you're only above and below, so it's going to be 2. If you have a double bond, what's the pi bond associated with that then? A double bond. What is that? How many bonds do we have there? Pi bonds specifically. 1. Yep, exactly. Because again, like you have 1, right? Because it's double, you get rid of 1, you have just 1 left over. You're pretty much just subtracting 1. That's the whole pattern. And then steric number is just gonna be, yeah, pi bonds is actually just gonna be 1 less than a double or triple bond. Yeah, 1 less than a double or triple bond. Steric number, or like steric or sigma bonds really, it just counts as 1. So this counts as 1. Double, that counts as 1. A regular single bond, that counts as 1. It just counts as 1, pretty much. And then pi bonds are only there in double or triple bonds. Pretty simple once you get it. Yeah, intermolecular forces. What is that? Highlight the inter parts. You knowing that prefix. H bound. No, you're getting there. Let's keep going. It's actually more broad. Intermolecular forces are, what are those forces between? Or what are they part of? Yeah. What are intermolecular forces or intramolecular forces? within atoms. For which one? Intra or inter? Forces within atoms. Is that inter or intra? Inter? Okay, do we agree with that? Anyone out there? Like, forces within atoms are inter? Do we agree? Yes? No? Okay. Actually, Natalie's right. It's actually intra. Inter is between molecules. So you'll have it between. It's okay. It's fine to have your friends back and stuff. So intra is just going to be within the atoms, pretty much. Wow, it's nice to see people sticking up for one another. That's cute, isn't it? Okay. Yeah, but intra is just the forces within the atom. So pretty easy, right? Once you know the prefixes and stuff. Do we have any questions? Or are we all good on this? We're all right? Yes? Good? Okay. Nice. Okay. So let's keep going. Those are the answers in case you missed it when I was saying it. Again, between, and then intra is within. Look at that. Okay, once we got that, okay, let's find the sigma and pi bonds for the following molecules, SO2, Cl, and I'll just draw it like that just in case you want to see it in a different matter. But anyways, how many sigma and pi bonds do we have from that? So let's draw it out first, right? SO. Actually, let's just do Cl on the side. I think that'll be a little easier. So once we have that, what does that look like? How many valence electrons are we going to have? Does anyone know? Like, how many does S have? How many valence electrons does sulfur have? Does anyone remember sulfur? 6. Yep, so you have 6 for that. And then you have how many for oxygen? 6. And then you have 2, right? So that's going to be 12. And then what about Cl? What's that going to be? 7, right? 7 times 2 is 14. So you're just going to add that all together. And once you add that, what do you get? Just adding, yep, 32. So once you get 32, and we put this all around the Lewis structure, what do we get? What do those bonds look like? For example, like S to oxygen, what type of bonds are we gonna have? 4 sigma bonds. Okay, and then, yes, exactly. And then, but how do we show that? Like, for S to O, how many, is that double bond, single, or like Cl to S, is that double bond, single bond? Can anyone tell me? All singles. Okay, do we all agree with that? Yes, no? Because Akash said all single bonds. Do we agree? Or do we not know? Yeah. If you're going S to O, you're gonna have what type of bonds? OC has double bonds. Actually, it's O to S, but yeah. Actually, you're gonna have a double bond, not all single. Yeah, double for O. Yeah, usually with like O bonds and stuff, like they tend to do have double bonds. So with this, how many sigma bonds are we gonna have? 2 sigma bonds? We have 2 sigma bonds or, okay, sigma bonds and then pi bonds, right? How many sigma bonds are we having here? Does Jorge said 2, do we agree or is there a different answer? I think it's 2. Okay, agree. Actually, I think you guys are thinking about pi bonds. Pi bonds is 2. Pi bonds is that double bond is 1. So that's 1 pi bond here. And there's 1 pi bond here. Right? So that's going to be 2 pi bonds here. But sigma's different. Sigma's any bond. Any bond that's attached to the central atom is a bond. And it counts as 1. So actually, essence is right. It's going to be 4 sigma bonds, actually. And the reason is because you have 1, 2, 3, 4. That's 4 sigma. And nope. Sigma bonds can be any bond, but it counts as 1 each time. Whether it's single, double, or triple, it's just 1. It counts as 1. So I think that's okay. Do we have any questions on that one? Because sigma bonds is just, okay, good. So let's do CH2O. What is that gonna look like? So we have CH, what's the valence electron on C? Does anyone remember? 4, right? Okay, so we have 4 plus how many valence electrons on hydrogen? What is that? Hydrogen. Yes, exactly. So it's gonna be 2. Scared me for a second there. So to say. Okay, what about oxygen? How many valence electrons? 6. Yep. So you add that all together, we get 12, right? So when we show 12 valence electrons on here, what is that gonna look like, and what are the sigma and pi bonds associated with that? Does anyone have an answer? Do we have any double bonds? First of all, do we have any double bonds here? 1. And where is that double bond? Does anyone know? CO. Yes, exactly. Because we just said, like, usually, like, if it's around, like, oxygen, nitrogen, and stuff, they tend to have more double bonds. So here we're having a double bond, right? And then, do we have any other lone pairs on the central atom, or is that it? Yep. So, are there any other lone pairs on the C? Or any at all? Do we have any lone pairs? No. Yes, exactly. There's no lone pairs left. So knowing this, what are the number of sigma bonds? 3? 3. Yes, exactly. Can anyone tell me how they got 3? How'd you get 3 from this? Yeah, sigma bonds are just the bonds itself. Yeah. So, yeah, 3 from the central. Yes, exactly. You're just counting the bonds on there. So once we found that, what about the pi bonds? Yeah, just like a double bond would just count as 1 sigma bond. And then what about the number of pi bonds on this? We have 1, 1. Yes, exactly 1, because there's only 1 double bond, right? So it's just gonna be 1. Pretty simple, pretty easy. Okay, and let's do the last one then, C2 and then H2. Yeah, lone pairs do kind of, no, I wouldn't really say, actually, yeah, it might. Because if you have another lone pair attached to the central, that counts as another bond on the central, right? So then that'll be counted as another sigma. But pi bonds aren't associated with lone pairs because there's no double or triple on there, right? Because it's just a regular lone pair. Pi bond can be for triple as well. So if you have a triple bond, then that's 2 pi bonds. Yep. So C2H2. So can anyone tell me how many valence electrons are we gonna have from that? 8. Okay. So do we have any double, triple, anything? Do we have anything? 1 double between C, a double. Okay, do we all agree with that? It's gonna be 1 double bond between C. Is that the final answer? Do we all agree? Yes. Okay, actually, it's gonna be 3. Now, can anyone tell me if they knew it was 3? Yeah, because you don't really need, because see, that's the thing, H to C, you only have 1 bond, right? Well, you can only have 1 because it's hydrogen, right? So in between this, you still need an octet. So there needs to be 1 over here and then 3 in between, so you can have a full octet of C, right? Because everything surrounding it is just hydrogen.
Okay.
Yeah, that's why.
Bye.
So yeah, once you notice, you're like, oh yeah, hydrogen can only have 1 single bond. So how many sigma bonds do we have from this? Does anyone know? How many sigma bonds do we have? 3, okay. Does anyone else agree with that? Or disagree? And Kosh said 3. Does anyone have any other answers? Or what about pi bonds too? 2. Okay. Central atom? Okay, for this one, you're just looking in between here then. Because there's no like genuine like central, because there's 4 of them, right? So then it's just spread out like like a line. So it's just gonna be the in between, right? Because there's only 1 in between, because it's odd, right? No more bonds. So we have 3 sigma bonds, and this someone said 1 pi bond. 1 pi. Okay. 2 pi. Okay, yes. Yep, it's gonna be 2 pi, not 1. And can anyone tell me why? Why is it? Why is it not 1 pi? Why is it 2 pi? Does anyone remember? Like, what was the trick or what was the pattern you do? Yes, exactly. For double and triple, you just minus. Yeah, it's a triple bond. It's gonna have 2 pi instead. And then you have a double bond. It's gonna be equal to just 1 pi. So, do we have any other further questions on this part? Sigma and pi bonds? No? Okay. And so I'm just gonna keep going then. That's the answer to that. Okay, now we're gonna label this. How many, and then for, okay, sigma bonds. How many sigma bonds do we have here then? And then how many pi bonds will we have? Okay, 11. And then do we agree with that? 11 sigma. Do we all agree? Is there a different answer? Yes. Okay, does anyone have anything for pi bonds? 3. Okay, 3. Do we all agree with that then? 3, okay. Yep, that's correct. Anyone tell me how they got that? How'd you get 11 and then how'd you get 3? And where? Where'd you get it? For like pi bonds, how'd you get 3? Because there's like so many lines here. How did you get 3? Okay, 1 bond equals 1. Yep. So what about pi? You have 1 here. Double bond. That's just going to be 1 pi. Just a regular single is just going to be a regular sigma bond. And that will just count as 1. And then the double and triple count as just 1. Yep, exactly. The 2 plus the 1 will equal to 3 pi's that we have. And then every other single one is just going to equal to just, you know, the 11 that we have. And you keep counting all them 5, 6, and stuff. Like, it goes all the way to 11, basically. So are we all good on that? We all got 11 and 3? Okay, I'm going to take that as a yes. Okay, yes? We're all okay? Okay. Okay. And then that's the answer. Again, I got this off of, I think, Organic Chemistry Tutor. So I think he's great for learning this. If you want extra practice, I highly suggest going to his YouTube channel. Yeah, they're pretty much awesome. Khan Academy is good too. I don't love it as much, but I love Organic Chemistry Tutor. Explains things extremely well. So that's how I learned how to do sigma and pi bonds myself when I first did this. So that's how you do that. And now just do number 4 really fast. And then once we reach 3 o'clock, again, like you'll have your little like potty break, and then we'll do Kahoot. So, electron pair geometry. What does that go to? Does anyone remember? Tetrahedral, exactly. So, what are the number of bonded atoms we have here? 4. And it goes down to what? Okay, 4, 3, 2. Do we agree with that? Yes? No? 4, 3. Yes, exactly. It goes down to just 2. What about the number of lone pairs we have? What does that go to? What are the numbers going down the row? 0, 1, 2, yes. Exactly. Again, you're just going all the way down to there. So what's the molecular geometries? 4 to 0. What is that going to be? Does anyone remember? 4 bonded atoms, no lone pairs associated. What's the molecular geometry of that? Just a regular... Okay. Actually, do we have any other answers? Because there might be a little confusion here, right? Start number 4. Does anyone remember? We have 4 to 0. Tetrahedral. Yep, exactly. It's just going to be tetrahedral for this one. There's no bent included or anything. What about 3 to 1? What do we have? If you don't know this now, you can try like memorizing it in like steric numbers. So start with like 3 and then tomorrow do 4 and then next day do 5. Like just keep doing it like every single day, reiterating it, and then over time you'll get it. Oh, sorry. Okay, but let's, okay. 2, 2. Okay, my bad. Okay, then yeah, that would be right then. That would be bends. And then 3 to 1. What is that going to be? Does anyone remember? You have 3 to 1, 3 bonded atoms, no lone pairs at all. Or I mean, 1 lone pair, sorry. 1 lone pair, what is that going to be? Does anyone remember? Yes, exactly. It's trigonal pyramidal. I can't really pronounce it, but you get the gist. Not bipyramidal, by the way, because I know some people might get confused. It's trigonal pyramidal. TP. Yes. So what are the bond angles with 4O? What's that going to be? Does anyone remember? Yes. Yes. 409. Yes. So 407 is actually not part of bond angles at all. So, and also if you don't know bond angles now, like it's really easy when you memorize it because it's all part of like the same degree for each steric number. It's just like, oh, if it's more or less than. And then, so actually Akash is right. It's actually going to be 109.5 for the first, and then the last two are also going to be less than 109.5. 104, I think that might be a typo. 104 is not part of the bond angles at all. So, yeah, this is what you would want to memorize. Again, this is in your book, so if you have any problems with this, you can't remember it. I actually have like my own sheet, so I might send a photo later, or I'll send out this PowerPoint. You guys can look at it if you really want to. So that's what that looks like. And do we have any, I don't think we have any questions on this, so I'm just going to keep going. So this should be pretty fast. London dispersal forces occur between which, yeah, I can go back really fast. Okay, London dispersal, yes, exactly. All, what specifically does it associate with though? London dispersal. Because I get what you're trying to say, Essence, like it goes with every single, but what is it specifically? Usually, like what does it go with? Like, what do you identify dispersion forces with? What type of molecules? Polar, nonpolar, metallic, covalent. Nonpolar, yes, exactly. Those are associated with nonpolar specifically. And again, Essence is right. Dispersion forces, it goes with every single combination. Like anything, it just goes together with it. What's the correlation of boiling point and intermolecular forces? What is the correlation? Is it inverse? Is it proportional? Is it higher bond, higher boil? Okay, do we agree with that? That's proportional? Yes? No? Yes, exactly. So you have a higher boiling point. You're also going to have a higher intermolecular force, which we will discuss which intermolecular forces are the strongest versus the weakest ones. And then what's viscosity? Does anyone remember what that is? Viscosity. Yes, no. This is just a straight up definition. Resistance to flow, exactly. What about polarizability? What's that? Does anyone remember polarizability? Again, it's another definition. This was like from like 6.2 or something. Yes, no. Do we not remember? Nope. Okay, does anyone else know? Polarizability. It has to do with creating something. What is that? It's in the word polar. You don't know? Okay. So with polarizability, it's basically a molecule creating temporary dipoles to attract other molecules. That's what ion or dipole induced means. Like you're creating temporary dipoles to attract other molecules, but it's very temporary, which means they're very weak. And then spheres of hydration. Does anyone remember what that was? Yes, no? This was in like 6.2 or 3 as well. Does anyone remember? Spheres of hydration. Spheres of hydration. That's a hint. Spheres. So you have C, you have H2O around it and stuff. Can anyone predict what that will be or guess? What is that going to be? Does anyone know? Yes, no, I don't know. I think you're thinking a little too far into it. It's actually just going to be a molecule surrounded by hydrogens. I mean, or like water molecules, really. That's what the sphere of hydration means. It's a literal sphere of H2Os, or water molecules, surrounding a molecule. Like, it's pretty, like, straightforward. Just, yeah, circle water. Yeah, and then what about average atomic mass? How do we find that? And that's for natural abundance, right? How do we find that? What's the equation associated? Yes, and then how do you do that? If you're given like mass or like natural abundance, how do you do that? Like they give you a mass, and they give you the natural abundance. How do we find that? And given that chart, what do we do? Yep, you change the abundance to a decimal, and then what do you do once you find that? What are you gonna do next? So you found the natural abundance, you add. Okay, do we agree with that? It's gonna be adding? Yes, no? Does anyone know? Like, you wanna chime in and say, help our peer out. Okay, does anyone want to say something? Like, multiply? Yeah, actually, you're gonna be multiplying. Yep, so you're gonna take the natural abundance, you divide it by 100, usually, and then you multiply it times the mass you're given. So you're gonna take this, convert that to just like decimals, then you multiply that times the mass. The isotope mass, really, because natural abundance, you're usually doing it with an isotope, right? Then add. Yeah, then you add all of it once you find those masses. I think that's what you're trying to say, yeah. So once you find those masses, you just add them all together. Speaking of which, so those are the answers to those. But actually, we're going to do an example of that. But rank these from the strongest to the weakest. What's the strongest one? Each. Okay, did we all agree it's going to be hydrogen? Hydrogen? Okay, anyone else? Ion dipole. Okay, different answers. Okay, I want to hear some more answers. Does anyone say hydrogen or ion dipole? Iron or H? Okay. Anyone else? Hydrogen. Okay, so actually, ion dipole is the strongest one. Ion dipole. I know that's hard to believe because you've always been of the formula. Yeah, it's just gonna be natural abundance in decimal form, the decimal form, and then you're gonna multiply that times the ionic or the isotope mass. And once you find that, you have your mass. You usually have like 1, 2, 3 of those you find, and you're gonna add all of those masses together, and that's how you find the average atomic mass. Yep. So ion dipole is the strongest actually. Hydrogen will be the second. Ion dipole, it's just an ion with a polar bond with it, and it just happens to be stronger than a hydrogen alone. So it's actually gonna be the strongest. What's the third one then? Ion dipole, hydrogen. What's next? What's the third strongest? Dipole, dipole. Okay, anything else? Anyone else? Agree, disagree? London? I don't know. Okay. Anyone else? London is first. Because I feel like you guys don't know ion induced either, and so you guys are like blanking. It's actually gonna be dipole, dipole. And those are polar bonds. Polar. And then the fourth one will be dipole induced. Yeah, induced, exactly. And dipole induced is basically, because I think you guys had trouble on this earlier in the session, is basically when a molecule makes temporary dip to attract other molecules. And the reason it's so weak is because it's temporary, it's not real dipole, because that's why dipole is stronger, because they're real dipole bonds. They're not temporary. They don't have to fake it, they're true. So, and then London dispersal, we already know that's non-polar, right? So that's going to be the weakest, pretty much. Do you have any questions? I think it's pretty straightforward. Yep, that's pretty much it. And then we're just gonna keep going. That's the chart. This is from your textbook too. So I think that's pretty helpful. And then, yep, so let's do average atomic mass. So you're using the natural abundance with this. How would we do that? Can anyone tell me the process? Like, what are you gonna do? Like, what are we doing here? Like, we have 84 seronium, right? What do we do with that? Yes, exactly. You're gonna multiply it. Do you multiply it as is, or is there something we should do first? Does anyone remember? Convert, yep, you're gonna change it to a decimal first. So once you've done all that, divide by 100. Yeah, for this one, you're gonna divide by 100 to get the decimal, if anyone's wondering, just in case you're like lost on that part. You're dividing by 100, and that's how you get the decimal form of the natural abundance. And once you multiply that by just the mass, you should get the atomic mass for that isotope. So what do we do once we have all that? Like once we have the answers to this? which I want you guys to do right now. What do you do after that? Once you have all the answers, you add all of them. Yes, exactly. So once we do that, what's our answer gonna be? So you can take out your calculator and start like multiplying them and stuff, and then finding the final answer. So once we do that, what do we get? Does anyone know? If you multiply this together, because that would just be point, I believe, 557 or something. Once you do that, what's the answer going to be over here? Does anyone remember? Yes? No? Yep, okay. Actually, yep, that's correct. It's supposed to be 87.2627. Do we all agree with that? Or is anyone confused? Like, oh, I didn't get that. I got like 70 something. Because again, it's pretty straightforward. Just following a formula to multiply it every single time, basically. Do we all agree? Do we all get that? Yes? No? Yes? Okay. Well, if you later on you're still doing it and you need help, you can just tell me. Again, it's just like another pattern. It's just the same thing every time. What about, okay, Cl2. What are the intermolecular forces in Cl2? What forces are we having? Are we having London? Are we having hydrogen? Are we having like ion induced? Like what are we having? Okay, we're having London. What else are we having? Or is that it? That's it. Yep, exactly. So with this, you're just having London dispersal. What about NH2Cl? What intermolecular forces are present? Right? Because now we have, well, all of them have London. We all know that, right? So you have London there. What else do you have? Or is that it? NH2Cl. What do we have with that? London. Anything else we noticed? Because we have a hydrogen, right? So H bond, yes. So you're gonna have hydrogen included. And when you have hydrogen, usually what else do you have included? Because that's polar, right? What do you have? What other force do you have present? Dipole, dipole. Yep, exactly. Dipole, dipole is associated with polar bonds, which means that you're probably gonna have it with hydrogen as well, for the most part. What about NCl3? We have London as usual, because we already know that. What else is included, or is that it? Just London? Is there anything else included? I think that's it. Okay, do we all agree with that? It's just London forces? London dispersal? That's it? Do we all agree? You don't know? Okay. Does anyone have anything else they think? Because that's right, it's not just London, there's something else in there. And we know it's not hydrogen, right? Because there's no H in there, obviously, so it can't be hydrogen. What else is in there? What kind of bond is this? NCl3. What type of bond do we have here? Polar, exactly. You have polar bonds. What type of forces do you have? You have a polar bond. What is that? Dipole. Yes, exactly. You're going to have a dipole-dipole bond. There's no hydrogen in this case, but it's still polar. So it's going to be a dipole-dipole and London dispersal forces. Are we okay on that? We all understand? Yes, any questions, comments, concerns? We're good? Okay, I think we're good, I guess. Like, yes? Yes? No? Okay, thank you. Alright. No, how is it polar? Okay, but this, again, you would find like different ways to find it being polar. Like, you can draw it out. In this case, like, you can like write out NCl and you can do it a bunch of times and figure out, oh, that's polar, because like it doesn't go all in the same direction. Or you can find it through electronegativities, like, oh, it's not all the same. You would figure out that it's not non-polar. It's polar. So again, you just have to find that on your own. Okay. Okay, let me see what else we have to do, because I think, okay, so I'm gonna extend the potty break until like, I don't know, like 3:10 to 3:15, and then we'll do the Kahoot, which is basically a practice test, and it's like 23 questions, and whoever wins it, yeah, and then this isn't even all of it. This is actually part of exam 3. like a good chunk of it overall, but there's some things I wish I could go deeper into, but that would take like 4 hours. So yeah. So I'm just gonna show you guys this because I think this is important to know. This is just sig figs, so know this. And I know you're like, oh, I already know sig figs. We're doing different types of sig figs with this. Because when you do moles to molecules, which I know you guys know how to do because we did that like a whole exam ago, instead you're going to be finding how many moles of salt or Na is in NaCl3. You're doing it more specifically now, like a mole concept. Not just moles to grams, molecules to moles. Like, it's more specific. How many moles of Na are in NaCl3? Like, that's how specific they're going. It's a different type of question, but the same concept. Okay, and then these are you guys know the zero beginnings, they never count. Leading zeros don't count, trailing zeros don't count unless there's a decimal. Zeros after non-zero numbers, digits always count. If there's a decimal, non-zeros always count. Okay, and then are we good on this? Because again, this is a review. We did this like a month ago, and usually like you guys know this because you guys don't have equation sheets. But are we all good on this? Yes, we understand. Yes, okay. Okay, this is just really fast review. Which are exact values, which is inexact? This is just a multiple choice question. So 1 and 2. Can anyone tell me which are exact values? A, B, C, D, or E? Or how many? Which ones are exact and which ones are inexact? I'm gonna give you guys a second to read that. So, exact values. Let's write that down here. What do we have? What are exact values? Okay, A and C. Do we all agree with that? It's gonna be A and C. A and C. Yep, it's gonna be A and C. And can anyone tell me why? Why is that A and C? What makes it correct? What makes exact values? How do you know? Because the rest of them, then like B, D, E, those are inexact, right? How do you know that A and C are exact? How did you figure that out? What pattern do we have with exact? Okay, yeah, you have the right. I understand what you're saying because you're right. But how do we know? Can anyone else like put into words? Yes, no, I don't know. Like if you don't know, just in case. Yeah, yes. Is anyone confused? Okay, so that's exactly what it is. Okay, yeah. So you guys are all like there in a way, but actually exact values are what can be counted. If you can count it, then it's an exact value. Like the 36,941, you can count that. I mean, it'll take forever, but you can count it. And then C, there's 893 stairs. You can count it. The monument is 169. You can't count that. Like you're already here. Like you can't go 1, 2, 3. Like you can't count the meters up above you. Like it's just too much. So exact values are values you can count. See, like exactly 893. Like that's how you would know. You can count it. What about number 2? Which values can you count? That would be exact. Exact numbers are numbers you can count. Things you can count. So which of these are exact? A, B, C, D, or E, or like a combination. A and E. Okay, yep, exactly. You guys are completely right. A, again, easy. Just count it across. You guys probably do that all the time when you drive to like Kennesaw or something. Fast track toll. Yep, it counts the way same as money. You can count money. It's the same thing. And then the bridge, you can't count the bridge. Like I don't think any one of you can just go on a bridge and be like, yep, that's 27.4 meters. And plus, people probably look at you like you're on crack or something because you can't do that. And then the mass, yeah, no one can do that. So again, A and E are exact values because you can actually count those. A and E. So do we have any questions with those? That's just a quick review. Pretty simple, pretty easy. Do you have any questions? Comments, concerns? Yes, no? No? Okay, you guys did a great job. We're gonna have a quick little potty break